Okay, hello, and so let us look how to use this definition of limit we just introduced. And so I just want you to give you an example of exercise of the type prove that the limit of this function and when x goes to x bar is equal to L. Okay, so okay, here I am. Sorry. And so the exercise is the following. Prove that lim. So, no. Prove that the limit for x going to 2 of x squared is equal to 4. Okay, here the first observation is the following. X bar and L are finite, so are real numbers. So for this sort of exercise, it can be convenient to use the metric definition with epsilon and delta. So we use the metric definition that says for every epsilon larger than 0, there exists delta larger than 0, such that whenever x is different from x bar less than delta, and x in E, but in this case E is equal to R, because x squared can be defined on all R, then f of x minus L, which means, okay, you write everything, f of x minus L, which means x squared minus 4 is less than epsilon in absolute value. Okay, so the solution is the usual one. The strategy is the usual one we already introduced for the case of sequences. So we say let epsilon larger than 0 be an arbitrary number. And so we search for the values of x that satisfy the inequality absolute value of x squared minus 4 is less than epsilon, which means that x squared is between 4 minus epsilon and 4 plus epsilon. Okay, so let us start to see what to do. First, we consider that the absolute value of x squared minus 4 is the product of the two absolute values x minus 2 times x plus 2. So first, let us suppose delta smaller than 1. Why can we suppose that? First, it is convenient because computations are simplified a lot. Then we are just looking for delta larger than 0 that fulfills the following condition. And so at the end, suppose that we find, I don't know, delta equal to 5. 5 is larger than 1, so this hypothesis will be denied, will be contradicted at the end. But this is not a problem, because if for any delta, if for delta equal to 5, this is verified, then it is verified also for delta less than 1, because this condition for delta less than 1 is stronger, is a sort of subset of condition, is included in the condition delta less than 5. Okay, so it is not a problem, it is not restrictive, okay? We will see it at the end. So, think of it, however, and then with delta is less than 1, this means that we are considering values of x that are between 1 and 3. Okay? And since they are between 1 and 3, we have that x squared minus 4 will be less than, I'm taking my conclusion from here, less than the absolute value of x minus 2 times 5. Because here the worst situation, the situation in which this absolute value gives the maximum, is when x is equal to 3, which is a strict upper bound for our x. So here I can put 5. Okay, why do I operate like that? Because here I have a square, which is nothing transcendental, but it is more difficult to deal with than x, okay, the linear power. So, then we look for this condition. So, we solve the inequality. Absolute value of x minus 2 times 5 less than epsilon. Indeed, this inequality due to this asterisk inequality guarantees x squared minus 4 in absolute value less than epsilon. So, what am I saying? I'm saying that this inequality here is simpler than this one, but it is stronger. So once this is fulfilled, this is fulfilled too. And why? You can ask why? Because of this asterisk. So once the second is fulfilled, the first is too. Okay. So, so as a choice, I can try to take delta is equal to epsilon fifths. Then we have that 0 less than x minus 2 less than delta, which is epsilon over 5, implies that 5 times x minus 2 is less than epsilon. So, therefore, for this choice of delta, we guarantee this one, that guarantees that the one we are looking for. So, now we want to choose delta, and it is then enough to choose delta as follows. Delta is the minimum between 1, which was the first assumption here, or let me put here delta less or equal, minimum between 1 and epsilon over 5. Of course, we don't know which is the minimum of the two, because here there is epsilon, which is an arbitrary number. Of course, when you think of epsilon, I recall you, think of a very small number. So, in this minimum, to fulfill this minimum, a good candidate is epsilon over 5. However, formally, we have to remember that we chose also 1 at the beginning. When delta is taken as the minimum of these two, then we have the two conditions fulfilled. The first one is that this asterisk that allows us to pass from a quadratic inequality to a linear inequality, so it is much simpler. And the second gives us the possibility of writing this. Okay, so we have to consider both. If you remember the lectures on sequences, this procedure of taking the minimum of the two deltas we proposed during the solution of the exercise, this procedure is pretty analogous to the procedure of taking the maximum between n bar 1 and bar 2 in all proofs of this kind for sequences. Okay, and this is the solution of the exercise. So we can conclude, therefore, for every choice of epsilon positive, we found a value of delta such that whenever x minus 2 being always larger than 0 and less than delta, then x squared minus 4 is less than epsilon. By the definition of limit, we end up, we have this conclusion that limit for x going to 2 of x squared is equal to 4. By the way, I perfectly know that all of you were able to say that. All of you already computed limits that are much more difficult than this one, and we will do too, okay? But this is another kind of exercise. This is not compute this limit. This is prove that this limit is equal to 4, okay? And this is very useful to let you understand what really is a limit, beyond all my considerations and so on. Okay, you deal with a natural function, a concrete function, and then you apply the definition. So, a pretty analogous exercise to this is the following, completely analogous also in the procedure for the solution. So, prove that the limit for x going to x bar of x to the power m is x bar to the m, where x bar is a real number and m is a natural number. If m is not natural, this becomes a bit tricky. Okay, and I will tell you what to do when we will study continuity and exponential. But however, it is not so natural, and this is homework for you, and so we can. So this is homework, and another exercise of this kind can be the following: given x bar in R, prove that the limit for x going to x bar of x to the mth power is equal to x bar to the mth power. Oh, sorry. This is the homework. This is sine of x. Limit of sine of x is equal to sine of x bar. And again, the solution is as before. So let epsilon be a positive arbitrary number. Okay, we want to solve this inequality. So we aim at solving the inequality epsilon strictly larger than sine of x minus sine of x bar. And we will use these strange formulas concerning the sum of a trigonometric function, and with this absurd name, which is Prostaphérèse formulas. Of course, you are not required to know these formulas by heart. It's really not so important to know them by heart, but you have to know where to find them. So, and this is equal to 2 times absolute value of sine of x minus x bar divided by 2 cosine x minus x plus x bar divided by 2. Okay? And this can seem to be a bit tricky, but so just formulas. I don't want to prove them now. Think of them. They are very well known from high school. So this is equal to 2 times, we use the elementary property of the absolute value of sine of x minus x bar divided by 2 times cosine of x plus x bar divided by 2. And now the first elementary inequality we use for trigonometric functions is that the cosine cannot exceed 1. So we have that this product never exceeds 2 times sine of x minus x bar divided by 2. Okay? And this is less than 2 x minus x bar divided by 2. And this is equal to x minus x bar. So I want to explain this. This simply comes, okay, let me move here. This comes from the immediate inequality sine alpha absolute value less or equal alpha. Okay? And now given epsilon, we can use we can find a delta. We can propose some candidate to be a good delta, and I just say, since at the end this inequality we want to prove is satisfied whenever x minus x bar is less than epsilon, because sine x minus sine x bar is less than this. So let me be clearer perhaps. So since, as we proved, sine of x minus sine of x bar is less than epsilon, is less than x minus x bar, in order to guarantee that sine x minus sine of x bar is less than epsilon, it is sufficient to choose x minus x bar less than epsilon, namely delta equal to epsilon. And this is the end of the exercise, and I suggest you another exercise. That is the following. Another exercise that says the following says, prove that for every x bar in R, the limit for x going to x bar of cosine of x is equal to cosine of x bar. Techniques are exactly the same. Okay, I stop here. This is a brief recording, but the next one will be extremely important. I will give you the basic theorem on limit. It is probably the most difficult theorem we have in the course. It is a theorem that reduces limits for function to limits for sequences, and it will be very useful from the theoretical point of view and also for proving that a limit that does not exist. So stay tuned, and I will come with these new topics.